So as always, I'm going to start our new chapter with the unit goals that we have, or chapter goals. And this chapter is about enzymes. And there is nothing more fundamental to biochemistry than the subject of enzymes. So it's a really important topic. It's a difficult one. And I want to tell you that it also fits very nicely with our last two chapters because we did protein structure and then protein function. Enzymes are almost always proteins. So this is simply an extension of protein function. This is just a different function for proteins. Now, before we get to these two unit goals, I want to tell you a single statement that kind of covers the entire chapter. And here it is down below. Enzymes speed up particular reactions. Sometimes we use more chemical descriptions to say the same thing. When we say enzymes speed up reactions, what we mean is they're catalytic. We'll come back and talk about that a little bit more. And when we say particular reactions, we say they are specific. So this is the kind of terms that we use in our unit goals. Describe the chemical principles behind how enzymes select a specific substrate and understand how enzymes make reactions go faster and interpret kinetic plots. So I often say that enzymes have a dual nature, and we keep revisiting this dual nature all the time. And the dual nature comes down to the way it speeds up reactions, that is, it's catalytic, and how it only works on very particular specific reactions. There's the specificity side. So I'd like to parse these terms out a little more by looking at a real reaction. Let's go down to the bottom of the page here, and let's take a look at this chemical species we have here. Let's say this is part of a protein, and that protein is a large protein. Maybe it's got several hundred amino acids. We won't pretend to show all of that, but as we know, proteins start at the amino terminus and end up at the carboxy terminus. And let's say this is a protein you ate and it was sitting in your intestine, and you needed to break this bond right here, and you wanted to do that all over, really everywhere. What kind of a bond is that? And here's a good question for you. If we were to use a water to break that center bond right here, what would the structure look like afterwards? That's a good practice. Take a minute, pause the video, and see if you can redraw this after you've broken the bond. Okay, I hope you had a chance to try that out. I'm not going to draw the whole thing, and you probably didn't need to either. But after we break this peptide bond, that's what it is, we change it from an amide into a carboxylate and an NH3 protonated amine, and we end up having two new functional groups that are both charged where there was one neutral functional group. So this is breaking an amide bond. And believe it or not, we have already talked about the type of enzyme that breaks this particular bond. This is only going to be catalyzed by the enzyme chymotrypsin, or at least that's one of the enzymes that can do this. Remember, chymotrypsin breaks peptide bonds after or on the C-terminal side of bulky aromatic residues. So this is a perfect example for us to talk about. It's certainly related to health and clinical situations. And it's also showing you the dual nature of proteins. Before we get back up to specificity and catalysis, I want to tell you about some terminology. One is this is a reaction, and we are going to take a reactant on the left, the intact protein, and change it into a product. So the P stands for product, but why do we have an S over here instead of an R for reactant? Well, biochemists always want to do things a little differently, and the reactant over here we now are going to refer to as an enzyme substrate. And that's it. We're going to no longer use the term reactant or R, and we're going to have S for substrate. It's really nothing more than that. So what about this particular bond that we're breaking at the bottom of the page? Well, we can tell you that a peptide bond is so incredibly stable that it's estimated that if you just left it in water, it would take about 500 years to break. I don't know how they estimated that. It's probably just a guess. But it's extremely stable. And for all intents and purposes, if you have it in your intestine without anything to break it, nothing's going to happen. It cannot break down, and you won't be able to get the amino acids out of your food. So catalysis is going to be sort of two things. Catalysis or catalysts like enzymes, they're going to speed up a reaction. And when we say that, we mean a lot. We might take a reaction like this, which won't happen in 500 years, and we might have 10 happen in a second or 100 in a second. So this can go very, very rapidly. The other thing about catalysts like enzymes is that the enzyme is regenerated. The catalyst is regenerated. If we started with a enzyme and it interacts with the substrate, makes it into product, then spits it out, the enzyme is exactly what it was when it began. So those are the two things that have to do with catalysis. Now, that's the chemistry, and let's make a note of that. And this is all about chemistry. But specificity is related, but it's very different. And specificity is selecting a particular substrate, and only that substrate. For instance, chymotrypsin in your intestine breaks down amide peptide bonds. It doesn't break sugar bonds. It doesn't break fat bonds. It only breaks peptide bonds. What's more is there's something about chymotrypsin that allows it to select only peptide bonds that follow big, bulky aromatic residues like the phenylalanine we have shown here. So this is not about chemistry, breaking bonds. This is about, does the substrate fit in the enzyme? This is about binding. And it's not about bond making or breaking. It's just about, does the key fit in the lock? Okay, we're going to keep talking about specificity and catalysis, the two sides of the coin for all enzymes, all through this chapter. So I wanted to take the time to really do it well. This is a little bit longer video than our typical unit goals, but we've dived right into some really important terminology. So let's leave it at that for now.